Hi all, welcome to fourth part of the video lecture on registers. So one of the fundamental sequential circuit. Okay, so already in the previous parts like part 1, 2, 3 we discussed what is a register in general, right, and the type of, so it is something which can store information as well as it can move information if needed, right. So if you are having that move operation, so then you can call it as a shift register. So it can shift the information or the move information towards right, then something like right shift, or it can shift the information towards left, right. So like that. So a shift register is a register in which the binary data can be stored. So by default registers can store information, right. So here also this can store information, and this data can be shifted to the left or right when a shift signal is applied. In our C program, we have this shift operator, shift as an operator, right. So binary operator, like, so if you are having some integer value, say int a equal to some 10, and there is another variable b. So what I'm doing is b is equal to a, say left shift, okay, one time, like that. So what will happen, or not to, so here you can say the counter, how many times you want to shift the data. So what will happen, this information a will be stored in your in some register, right. So we assume so. Let it be a 8-bit register, and what is this 10 in binary? It is 1010, right? As it is 8-bit, let me fill the remaining position with a 0. So like that, the information will be stored in some CPU register. So actually it is in main memory, right? This A is side and different. From there it will be fetched, and it will keep that information in some register, because for CPU to do some operation, this information should be there in the register. So that idea also I discussed already. So now suppose the information is available in some register. Now internally what will happen is this register is going to be shifted left, right. So this register is going to be shifted left means, right, what will be the output. So the information is to be shifted left. So every bit will move on position towards left, or you can do it right towards also. Anyway, I taken like that. So what will happen, the most significant bit, this bit, so when it is moving, so this bit will move like this, but there is no space to hold this bit, right, because it is already in the MSB position. So we will ignore, this bit will be ignored or something. This we will lose this information, right. So there is no other way. So there is something called a rotation, where you can feed this information back to the least significant position, but this is not rotation. Anyways, rotation also involves shifting. Okay, so that's all. And now this bit will come to the place of this bit, so that this will be 0, and this 0 will come here, right. So this 0 will come here, and this 0 is going to come here. So that only 3 zeros. The most significant 0 is coming out from the register. Now it is not there, right. Now this 1 will come here, so that there is 1, and this 0 will come to the place of 1, and this 1 will come, and this 0 will come like this. So 1 0. Now there is one space is vacant, right, because the 0 already moved towards this left. So what about the space here? So by default in C, if it is a left shift operation, this empty space is being filled with a 0. So by default this will be stored with a 0. Okay, so that is how they are implementing. So this is what we are going to see, right. So who is doing this shift for you? So that is nothing but our shift register. So now this register R1 should be a shift register, so that it can store information as well as it can shift. So accordingly, if the operation on so it can do this compilation and assembling, that time it will understand what kind of operation it is. Accordingly it will allocate registers during execution of the program. Okay, so that is the idea. So if it is a shift register, it can do this automatically, and the implementation details we will see how it is implemented. Now so you got the idea, right? Similarly, right shift, here you can specify the count, how many times. So this is something C, based on C programming I am saying, but maybe in different language it will be different. Anyways, the on background the computer will be doing something like this for you. Okay, the syntax may vary from language to language. So the bits shifted out at one end of the register may be lost. This is what I am saying. This bit may be lost, but if you want to retain, you can instead of implementing it as shift, you can implement it as a rotate. By default, it will be lost, right? So, or if the shift register is cyclic in type, this cyclic shift register is what I told, like the rotation. So this cyclic shift register can do rotation, right? So this is nothing but rotation operation. So something we already seen. Yeah. So bits shifted out at one end can are shifted back in the other end. So this is what I was saying. This will come over here if it is rotation, but for the time being it is not rotation. Okay. So anyway, all are variations of shift register only, and that how that feedback connected, that matters here. Yeah, that about it. Now this is something we already seen, and I'm asking you what are all the shift registers here. So who are all doing that shift operation? You can see that here it is shifting information towards right, so it is shift register. Here information is shifted towards left, right? Here also you are reading the data parallelly, but still information you are shifting right. But see here in these two cases, data is coming serially and data is going out serially in after doing shifting operation. But here data is coming into the register in a parallel way. So all bits will be stored into the register simultaneously, and but we will take the data out from the register in a serial manner. And that time definitely that shift will be there on the background. Here also you can see the data is inserted in a serial manner. So definitely that shift will be involved. But when we want, you can take out the data in a parallel way. But see, and this is not shift register, because here you can see it's very clear, right? Data is taken into the register in a serial manner, and we are taking the data out from the register also in a serial manner. Then what is the relevance of shifting there? So there is no shifting. So parallel in parallel out. Hope you remember, right? This is our PIPO register, right? And that is where we don't have this shift operation. And this is rotation again, and rotation also, that right shift and the last bit will come here, and rotate left means left shift and the last bit is something like anti-clockwise and clockwise rotation. Yeah, so these two things are also shift register. So except this PIPO register, all others are shift registers. So this is a typical construction again taken from NPTEL. A shift register is a register in which the binary data can be stored and the data can be shifted to the left or right when shift signal is applied that time. So the new bits get shifted in, and the bits shifted out typically get lost. So unless it's implemented as in a cyclic way, right? So it can be constructed simply by connecting the D or SR or JK flip-flop in cascaded manner. Okay, so hope you know. So the bits are to be forwarded, right? So that is the purpose. So you can use any of the flip-flops, say D or SR or JK. Okay, so they have to be connected one after another in a cascaded manner. So like this kind of a configuration is what we call as cascading. So one after another we have to connect them, and you know SR and JK, two inputs will be there, and accordingly I have to explain. So the figure may be slightly complex also, but you can just instead of this D you can use them also, like two inputs will come, that's all. So that you have to give correctly. So that about it. But by most of the default implementations are based on D flip-flop only, because that is enough. We just want this information to come out here, right? We don't have to set or reset SR and JK, we have to do like that. Okay, so that also will work, but D flip-flop is something by default we are using. So here you can see a 4-bit shift register. Basically 4-bit shift register means it should store 4 bits, also it should do that shifting operation over these 4 bits. So that is the idea. And now you know already that a single flip-flop, D flip-flop, if you are using, it can just store a single bit only, right? So that what is giving as input to this D flip-flop will come out in the output line, right? So that about it. So single flip-flop can do only one bit storage. Flip-flop is nothing but a 1-bit storage, right? So for storing as well as shifting 4 bits, we need 4 flip-flops. So those 4 flip-flops are connected like this, and see all are controlled by a common clock also, and the data is coming serially one after another, and whenever the first bit is coming, that will during the second bit, after the second clock pulse, this bit will come here, because this output is connected as input to this. So whatever coming as the output of this one, for example, if I am applying something like 0 1 1, first I will apply this one, right, starting with, because I want it as the MSB last position I want, right? Anyway, I just want to maintain this order. So 1 I will give here, so that this after the clock will go like this, right? At every rising edge of the clock, you can see that this is a rising edge triggered, right? Positive edge triggered. During that 0 to 1 transition, this will be this particular flip-flop will be triggered, and this one will just come out, because you know D flip-flop, the output to Q1 is nothing but T1. That is something we already see. Now you are serially applying one after another. Then the second one you will apply, right? So this this is already here, right? So now you are applying the new one, I mean this one. Now what will happen is, during the next clock cycle, all the flip-flops are triggered simultaneously, but the last two flip-flop there is no input. So even though it is triggered, just a 0 will be there, and that 0 will. So we typically initialize with a 0 for everyone, okay? And that initialization, yeah, you can do in your own way, but that initialization is not shown here. So what will happen, that during the next clock's rising edge of the clock, all the flip-flops are triggered. So as a result, for this second flip-flop, this one is the input. As a result, it is triggered, this one will come out. And for the first flip-flop, it is 1. Both will work simultaneously, and after that, this one will come here. Okay, so it is the current picture. You feel like there are 3 ones, but actually I processed only 2 ones, right? So this one actually indicates that the input I didn't withdraw so far, right? So maybe the next bit is coming, so next bit is 0, and that time this will change it to 0. And when this change will reflect over here, and that will happen only during the rising edge of the next clock, so like that. So what will happen, this one will be shifted here, this one actually moved, and this one will be shifted here, and this 0 is going to come here, something like this. So like that, the shift operation. So far we stored 0 1 1, and now one more 1 remains, that's all. So whenever this one is reaching at the last flip-flop, that will keep coming out in the line. So if you can connect some bulb here, you can see that it is going to that during that one, it's a high voltage, it will light you, give that light, right? So 2 times that light will blink, and then see light will off, and again like that you will get that feel. So this is how it is being connected. And just a simulation of a shift register. Assume initially that the register holds the data. Initially that the register holds the data. So I already told you, you can initialize it with a 0 0 0 0, as there are 4 flip-flop 4 zeros. Now suppose we apply, so how we are initializing, that is not shown here, or just apply that 0 for 4 times, that will happen anyway. And now suppose we apply one input to the first D flip-flop. So this one is applied, so that this one is supposed to come here, but that will happen only during the rising edge of the clock. Okay, it will not do it random. So here that is illustrated, that first one I applied, right? Then what I am doing, so I am just waiting for the rising edge of the clock pulse, and this is going to happen, and during that moment, so this is our input, our input is 1, so that is what is means. So what was our actual input, the full input, if you are looking over different rising edge of the clock, so here you can see a 1, then this is the next rising edge, here you can see a 0 for the input, next rising edge 1 as the input, again 1, see input line is high, right? That is why I am saying. So again 1, right? Now during the rising edge, input is 0, so next is 0, again during the rising edge, so 0 0. So this is how I am giving the input. Keep that in mind, we need it finally. So it is something like 1 0 1 1 0 0. So right now we applied only the first one, okay, that about it. And after that, you know what will happen during the rising edge of the clock. Anyway, I am removing this input, actual input you understood, right? So 1 0 1 1 0 0. So this is our input. Let me write the actual input. From the diagram I am tracing, first clock it is 1, then 0, then 1 1 1, then 0 0 0. So like that I am giving the input, so keep that in mind. Now during the first clock cycle, the first flip-flop, all of them will trigger, only the first one can do something different, right? So what will happen is, this one, this will be triggered, and this 0, this one will come here. Now for the second one, this 0 is the input, right? So during when the clock is triggered, only 0 it can see, not this one. This one will come after some small delay within this D flip-flop, right? So it can see only this 0, so that 0, so this one actually came here, right? Similarly, this 0 is going to come here. So this is what is happening during the first clock cycle. Okay, clear. Now in the next rising edge of the clock, so after that clock, this is how you can see the configuration, right? Hope that one is shifted. Now what is this one? This one is saying that so far we didn't supply any new input, right? So new input, next bit was actually 0. So we are going to apply it. So till that one will be retained. Okay. So the actual sometimes we call it as the but state of the flip flop. So if you are looking at the state diagram, something initially the flip flop was something like this. Now during the first rising edge of the clock, this is going to happen. Okay, now can you guess what will happen during the next clock cycle? We are going to see it. You know that shifting will happen. This 1 will come here, this 0 0, this 0 we will lose, and here the next input is, hope you remember, 1 0 then triple 1 like that, so that also 1 like that. Okay, so anyway 1 1 0 0 is the next state. We are going to see it. So that 0 is being applied during the rising edge, that 0 come out, right? Then it was 1 when I am applying it. After, I mean this is a status, I mean state before the clock. After the clock only this 1 will come here, and this will be triggered, and 0 will come here, and this will be triggered, and this 1 will come here. So like this, 1 1 0 1 0. Hope you understand it, right? It's a very simple process. You can trace the remaining portion only. Portions. How it is continuing, that our input is something bigger, right? 1 0, then triple 1 triple 0. So it will process, and one by one the final output you will get. Output is nothing but what it is, the last flip flop is giving us the output. Anyway, in between there are so a few more steps I tried to explain. Anyway, this is what we saw already. This was the initial state of the flip flop, where all of them are initialized with a 0. Now the input is shown here. You can see during different clock pulse, the input is like 1 0 triple 1 triple 0. This was your input, hope you remember. And how it is doing its task. Initially it was, this is the initial value, right? Whenever I am applying the first input as 1, so this 1 will come out as the, so this is like this, and this 0 will come here, and this 0 will come here. This is shifting, and this 0 will come, and this we will lose. Okay, now during the next clock rising edge, we already have that input line as 0. So what will happen? This 0 will come here. The empty space. Actually, we have to shift these bits. This 1 here, this 1 0 here, and this 0 here. So we will lose this bit. We can't do anything. And then finally this new input will come here like that. Okay, so I hope that you can follow now. What will happen in the next clock cycle? This initially this is something like this 0 shifted here, this 1 shifted here, this 0 shifted here. We will lose this. So this last bit we are losing always, because its size is small, that's why. By default right shift, we are not talking about rotation, so we will lose one of the bit, right? So that's also, now this new input 1 will come here like that. So how many states it's gone through, how many unique states it's gone through? It is like a 0 to 7, right? So 0 to 7 means there are some 8 unique states it's gone through, and that's a nice concept. We will see it again. So this is a typical diagram of a serial in, serial out. So input is coming in a serial manner. Also the input is supposed to come out of the circuit in a serial manner. So we can call it as SISO, serial in, serial out register. And this is a diagram, and it's showing like figure 8.3, and this figure numbering and all I didn't done. I taken from the textbook as a screenshot. That's why it's looking like this. The figure shows a 4-bit device implemented with a D flip flop with the 4 stages. This register can store up to 4 bits of data. Yeah. So now you can extend it to 5-bit SISO register, where 5 flip flops will be connected in a cascaded manner like this. That's all. And this is a something like a logical symbol or a block diagram kind of thing for a 8-bit SISO register. So what is going to happen? 8-bit is serial in, serial out, right? So this SRJ means shift register. S for shift, RJ for register. SRJ means shift. That is your S register. Shift register. And what is this 8 means? This flip flop is, this register is capable of handling 8 bits. So 8-bit storage it is providing. Okay. And this is a shorthand notation. So whenever you are seeing something like this, that means some shift register, SRJ shift register is being used. And what kind of shift register? That is clear from the diagram. Data in, in a serial manner, right? Because there are no multiple lines. Multiple lines typically says that it is done in a, I mean, input is given to the circuit in a parallel way. Okay, anyway, here the diagram itself says that it is serial in, and just only a Q7, through that you can serially take the data out. Okay, so 4-bit is what we've seen so far. Now you can see that 8-bit, or you can try yourself. That diagram and all not given, so this is just a logical symbol or block diagram kind of thing, and data is coming, data is going out. So serial in, serial out, SISO SISO shift register. Yeah, thanks for watching. If any doubt you can ask me. Yeah, thank you.